So let's look at solving this system of linear equations using the Gauss-Jordan algorithm. Essentially, we've got some simultaneous equations. Now the first thing we want to do is to make sure each of the equations that we have our x and y terms on the left hand side and our constant terms on the right hand side. Now you notice that's the case in the first one that we have here, but not in the second. Okay, so we just write that down. We've got 3x minus 2y equals 2 as our first, and the second is x plus 4y. But then putting our constant term over the right hand side, we have negative 8. Now we can produce an augmented matrix. Okay, so each of these numbers we put in there, so 3, negative 2 and positive 2 for our first row, and the second row 1, 4 and negative 8. Now the first thing we want to do in using this algorithm is to make sure, or if there are any rows that contain 1s as their leading entry, put that at the top. Okay, at the moment our first row has a 3 as its leading entry, but the second row has a 1 as its leading entry, so we can just do a direct swap in our rows, and that doesn't change anything in terms of the equations. It's just swapping those rows. So we'll put our 1, 4, negative 8 first, and then 3, negative 2 and positive 2. Okay, once that's in place, if we can, it's not always the case that there's a 1 as its leading entry, but if it is, then we do that. The next thing we want to do is, in our first column here, make sure every other entry is a 0. Okay, so this 3 needs to change to a 0. And the way we do that is to perform row operations. Okay, we're going to utilize the fact that we have a 1 here to change this 3. So what we do is we multiply our row 1 by negative 3, because that will change this to negative 3. 1 times negative 3 is negative 3, and then add that to positive 3 to give 0. Okay, so we're not changing the first row, it's going to stay the same, but our second row is going to change to something which is row equivalent. Okay, so once we multiply row 1 by negative 3, we add that to row 2, and that then becomes row 2. So it's a good idea over the right hand side when you're working through it is to do the operations. It's easy to make numerical errors. Okay, so multiplying each of these elements or entries by negative 3, we have negative 3, negative 12 and 24. We're going to add that to the second row. So writing the second row here, 3, negative 2 and 2, and then adding. Okay, so we've multiplied by negative 3, and then we're going to add it to row 2, so we have 0, negative 14 and 26. This then is our new row 2, so we can write then again our new matrix: 1, 4, negative 8, 0, negative 14 and 26. Okay, so our first column's good. The next thing we want to do is, for our next row that we have here, change its leading entry to a 1. And the way we do that is multiply that entry by its multiplicative inverse. Okay, remembering we want to change it to a positive 1, so we need to multiply it by negative 1 over 14. Okay, so we write it as negative 1 over 14 times row 2 becomes our new row 2. So in doing that, we have 0, 1 and negative 26 over 14. So each of those elements gets multiplied by that. So you'll notice that the order is important in the way we do it. Okay, notice that by multiplying that, when we multiply by 0 in the first entry here, it doesn't change it. So we still keep that 0 there, which is really important. Okay, so our new matrix that we're going to have is 1, 4, negative 8, 0, 1, and negative 26 over 14. We can simplify that to negative 13 over 7. Now that its leading entry is 1, all other zeros in that same column must be 0. So our 4 needs to change to a 0. So we're going to do a similar thing in changing row 1 the way we changed row 2 up here using this operation. So in order to change this to a 0, we need to multiply row 2 by negative 4 and add it to row 1, and that becomes our new row 1. Now you'll notice that by doing that, the 0 stays as 0 when we multiply it by negative 4, and when we add 0 to 1, it stays as 1. So the 1's not going to change in this operation, only every other element. Okay, so we're going to multiply, so 0 times negative 4 is 0, 1 times negative 4 is negative 4, and negative 4 times negative 13 over 7 will be positive 52 over 7. Okay, we need to add those to our row 1, which is 1, 4, and negative 8. Adding them vertically, 1, 0, and adding these together, negative 8 we could consider as negative 56 over 7, so that we can add these together, and that gives us negative 4 over 7. So that's our new row 1. So we have 1, 0, negative 4 over 7, and then 0, 1, negative 13 over 7. What we have here then is our matrix in reduced row echelon form. Okay, satisfies all the conditions. Our leading entries are 1, and every other entry within those is a 0. Okay. Now, how do we? The way we read our solution off is then we could translate this into an equation for each of them. All right. This first one would be the same as, because remember the first entry here is the coefficient of x. So we've got x plus, this is 0y. Okay, I'm just writing out in full for the sake of visualizing it, and that's equal to, remember this is our right hand side, okay, that's the right hand side of our equations, negative 4 over 7. The second row is going to be 0x plus 1y, or y, equals negative 13 over 7. So our solution is x equals negative 4 over 7 and y equals negative 13 over 7. Okay, a fairly straightforward example to give you the idea of what we need to do in this method. For simultaneous equations involving two unknowns, it's probably not the easiest way to go about it, but it's a useful way to demonstrate how to go about solving it. So we're going to have a look at the next example now. What we have here is a system of 3 equations in 3 unknowns, and that's where it does come into its own. It's a handy method, but we'll look at that in the next video. Okay.